Welcome to the final installment of our three-part lecture on improved filters. This lesson explores the concept of digital filtering. By no means are we limited to filtering in hardware. We can also perform filtering after acquiring the signals in software. Let's consider here a relatively static signal. In this case, it's a discrete signal, so maybe a signal that was acquired by my Arduino. It's pretty straightforward to see that I can do a good job of removing the noise by simply averaging the signal with respect to time, or in this case, with respect to the discrete samples. So I can take the mean of my signal and do a pretty good job of removing the noise. In red then would be the true value of the signal, and by taking the mean of the data that we have acquired, we've effectively removed the high frequency noise. If I have a dynamic signal on the other hand, so the signal is again discrete, but there's some frequency content associated with this signal, I can't just take the average. That'll effectively give me the DC offset of my signal, but I'll lose all the frequency content and related frequency information. So what I want to do instead is what's called a moving average filter. A moving average filter that creates a window. In this case, I have a window that has captured the first 3 data points. Inside that window, we'll take the average of those data points, and then we'll move on. So the next step, the window slides over to the next 3 data points, takes the average, slides over to the next 3 data points, takes the average, and continues throughout the entirety of the data set. So the frequency content of our signal, that's going to ultimately drive L, the length of the moving window that I'm sliding across my data set. So this is what's referred to as a moving average filter. And as an example, if we take a 2-point moving average filter, so our length would be 2, and this box would capture 2 points at a time, the output would be equal to y sub I is equal to x sub I, each data point, plus the preceding data point, x sub I minus 1, divided by 2 for the 2-point moving average. If I wanted to do a 3-point moving average, as I was showing here, I would take 3 points divided by 3. A 4-point moving average would have 4 points divided by 4, and so on. As we take more points with our moving average filter, so a larger L, this will lower the cutoff frequency of the filter. And this moving average filter is operating as a low-pass filter. As we noticed with our static data set, when we take the average, we remove all of that high frequency content. So this moving average filter operates as a low pass filter. To implement a moving average on something like an Arduino, we're going to keep all of our data in an array. Then we'll continually update the data that's in that array. Here we have an 8-element array, so L will be equal to 8. Each time we capture data from, say, one of our analog to digital pins, we'll store that data in one element of the array. So I have something like 23, 30, 25, 15, 13, 12, 17, and 19. Then I take my next data point and replace the respective element in the array. So maybe next time through I have a 21. Then I keep updating the elements in this array because I'm only interested in the last 8 data points to calculate my moving average. So I'm continually writing data into this array and looping through it. Then in terms of code, I'm going to sum the elements of this array, and my average value will be that sum divided by L, the length. So in this case, I'll sum the 8 elements and divide by 8. There are certainly more clever ways of accomplishing this task. For example, we could perform this division by simply bit shifting. So bit shifting all of our elements to the right by 3. So this will do the same thing as dividing by 8, but this is a rather fast way of performing that calculation on something like a microcontroller. If you're analyzing your data after the fact in something like Python or MATLAB, the move mean function will perform this moving average for you. So here you see help move mean. If you ever have questions in MATLAB, just type help and the name of the function. And we see move mean takes 2 inputs, x, which is our array of data, and k, which is a scalar number describing L, effectively, the length of our window. Let's now run through an example where we implement a moving average filter on data acquired with something like an Arduino. We'll begin with a true known value. So here I have a y equals mx plus b line where the slope is equal to 0 and the y-intercept is equal to 2.5. I'll then add noise on top of that signal, and this will represent data that I might acquire with my Arduino. So I have the signal with a high frequency noise component on top of that, in this case, just a simply DC offset. If I run something like a mean in MATLAB, taking the average of all the data here, I'll recover the original true signal of 2.5 with a slope of 0. So for a static signal of this nature, I could implement a moving average, but I could also just take the mean of the entire data set, giving me, in this case, the DC offset of 2.5. The true benefit of the moving average filter is in looking at dynamic signals. Here we have an analog signal, so this signal is with respect to time, and this is a sine wave with an amplitude of 5. So I go from -5 up to +5. If we pass this signal through a half-wave rectifier and digitize the signal, so we now have a discrete signal, we'll get something that looks like this. So now I have 200 data points, discrete measurements, and they're now rectified. So going from 0 up to 5. So this is the true discrete signal measured by our Arduino, but in reality, there's noise present, right? So here's that same rectified signal, now with noise, high frequency noise, added on top of that signal. As we discussed, if I take the mean or even the RMS of this data, I'm only going to get effectively the DC offset, say with the mean here. I'm not going to be able to do anything in terms of filtering the noise. So instead, what I'll do here is implement a moving average filter. And again, in MATLAB, we'll use the move mean function to perform that task. So here's the output of the moving average filter, where I have a window length of 1. And you'll notice the data is unchanged, right? Because now I'm taking the average of one data point, so there's no change in the output. Here's the output of the moving average filter with a length of 2. So as the window traverses across the data set, I'm taking an average of 2 data points at a time and plotting the result here. Here's the output when I increase that window length up to 3. When I increase that window length up to 6, and if I take a moving average window with a length of 10, I get the output here. For reference, I'll go ahead and plot that analog signal on top of our filtered digital signal, and you'll notice the results are pretty good here, using a window length of 10 for a moving average filter. As we mentioned earlier, this moving average filter, this behaves as a low-pass filter, and you see that, right? Here is our half-wave rectified signal, both the analog signal with the filtered discrete signal behind it in blue, and we've done a nice job of removing that high frequency content from our half-wave rectified signal. So our moving average filter is acting as a low-pass filter, and the length of that window, which I'm sliding across my data, needs to be chosen based on the frequency content of the data that I'm attempting to filter.